The moon looks close, only 3 days away by rocket, a familiar grey face hanging in the sky since before humans existed. But if you stepped outside on its surface right now without a suit, you would die in under 2 minutes. The vacuum would rip air from your lungs, radiation would tear through your cells, and razor-sharp dust would grind every seal, every joint, every machine into failure. That is why the safest place to live on the moon may not be on the moon at all. It may be beneath it. Deep inside ancient volcanic tunnels, sealed away from the sky, humanity's first lasting home beyond Earth might resemble not a shining city, but a buried industrial cave. And daily life inside it is worse than you think. If you enjoy deep dives into how strange humanity's future off Earth might really be, take a moment to hit that like button and subscribe. It genuinely helps this channel more than you know. Now, settle in and get yourself comfortable. Let's begin. Step outside tonight, find the moon, and hold up your thumb. You can cover it completely. That tiny grey disk sitting behind your thumbnail is roughly 239,000 miles away, close enough that radio signals from its surface arrive with a delay of just over 1 second. Close enough that a spacecraft leaving Earth can reach it in about 3 days. Close enough that 12 human beings have already walked on it, planted flags on it, driven electric cars across its plains, and come home again. No other world in the solar system feels so approachable. The moon has been the setting of nursery rhymes, ancient calendars, love songs, and centuries of astronomy. It follows you home when you drive, it hangs in family photographs, it defines the months. It is, in every emotional sense, humanity's second address. That familiarity is a lie. Not a small lie either. It is one of the most dangerous illusions in the entire subject of space exploration, because it makes the moon feel like a place that could obviously, eventually, be lived on. A slightly harder version of Antarctica, a colder version of the Atacama Desert, a quieter version of the top of Mount Everest. Somewhere difficult, sure, but somewhere a person could reasonably imagine walking out of a front door in the morning with a mug of coffee to check the mail. That mental picture is wrong at every level. If you stepped through an airlock onto the lunar surface right now, wearing ordinary clothes, you would be dead in under 2 minutes. And for most of that final minute, you would not be conscious to know it was happening. Start with the air, because there is none. The moon has no meaningful atmosphere at all. What it has is an exosphere so thin that individual atoms of gas travel long ballistic arcs across its sky without ever colliding with each other. The vacuum at the lunar surface is deeper than the vacuum inside a modern particle accelerator by roughly an order of magnitude. It is the emptiest environment a human being can practically be exposed to. And that emptiness is not a passive absence, it is a physical force. The air inside your lungs is under pressure. The moment that pressure has nowhere to push against, it pushes outward. Gas dissolved in your blood, including the nitrogen you have been quietly carrying around your whole life, begins to come out of solution like fizz from an open bottle. Your saliva boils on your tongue not because the moon is hot, but because water at zero pressure boils at any temperature above freezing. Consciousness fades in something like 15 seconds. Death follows shortly after. That is the vacuum, and unlike every other hazard on the moon, the vacuum does not care what time it is. It does not care where on the surface you are standing. It does not weaken. It does not fluctuate. It is simply the baseline state of everything above the regolith. At every latitude, for every second of every one of the roughly 4.5 billion years, the moon has existed. Every human being who has ever stood on the lunar surface has stood inside a personal bubble of Earth pressure, wearing a suit that separated them from instant death by a few millimeters of woven fabric and a sealed helmet. Take away that suit and you are not on the moon anymore. You are in space, and space is trying to kill you. Now add temperature. The moon rotates on its axis about once every 29.5 Earth days. This means a single lunar day-night cycle lasts nearly a month. The sun rises, tracks across the sky for roughly 2 Earth weeks of continuous daylight, then sets, and darkness falls for another 2 Earth weeks. There is no atmosphere to buffer any of it. During the long day at the equator, the surface temperature climbs to around 120 degrees Celsius, hotter than boiling water. During the equally long night, in the same location, the temperature falls to roughly minus 170 degrees Celsius. That is a swing of nearly 290 degrees between the same rock in sunlight and the same rock in darkness. In permanently shadowed craters at the poles, some regions are colder still, approaching minus 240 degrees, among the coldest naturally occurring temperatures anywhere in the solar system. For a machine, this is brutal. Materials expand and contract, seals crack. Electronics that were designed for one thermal regime have to survive the other one only a few hours after the Terminator passes overhead. India's Chandrayaan-3 lander went silent after a single lunar night and never woke again. For a human being, the numbers are simply unsurvivable. Your body has to sit inside a narrow window near 37 degrees Celsius to keep functioning. On the sunlit lunar surface, the ground beneath your boots is hotter than an oven set to bake. On the night side, it is colder than any freezer ever built for terrestrial use. And these extremes exist side by side, separated only by the shadow of whatever rock you happen to be standing behind. A boot in sunlight and a boot in shadow can be experiencing a temperature difference of hundreds of degrees at the same moment. Then there is the radiation, and this is where the moon's familiarity really breaks down, because radiation is invisible, silent, and its damage is cumulative rather than immediate. On Earth, two thick shields protect every living thing. The first is the atmosphere, roughly 100 kilometers of gas that absorbs and scatters incoming high-energy particles before they can reach the ground. The second is the planet's magnetic field, which deflects the charged particles that make up most of the solar wind and a large fraction of the cosmic ray background. Between these two shields, the natural radiation exposure of a person walking around on the surface of the Earth is small enough that our biology has evolved to tolerate it without much complaint. The Moon has neither shield. It has no significant atmosphere and no global magnetic field of its own. That means every galactic cosmic ray that would have been stopped by Earth's air and every solar particle that would have been swept aside by Earth's magnetosphere arrives at the lunar surface undiminished. Astronauts on the International Space Station are exposed to roughly 100 times the radiation dose of a person on the ground. Astronauts on the lunar surface would be exposed to several hundred times, depending on solar activity. And during a solar particle event, the sudden burst of high-energy protons that erupts from the sun during a large flare, the dose rate on the lunar surface can spike to lethal levels within hours. Apollo astronauts were, in a very real sense, lucky. Their missions were short, measured in days, and no major solar storm hit during any of the 6 landings between 1969 and 1972. If one had, the crew on the surface would have received doses capable of causing acute radiation sickness inside the same suit that was otherwise keeping them alive. For a short visit, the numbers are dangerous but manageable. For a permanent resident, they are catastrophic. A human being living on the exposed lunar surface for a career of years would accumulate radiation doses far beyond any occupational limit set for workers in nuclear plants on Earth. Cancers, cataracts, damage to the central nervous system, damage to the cardiovascular system. The biological consequences pile up in a way that no shielding built from the resources of a small habitat can fully prevent. And unlike the vacuum, radiation does not stop at the wall of a pressurized tent. It slices right through thin metal, right through most plastics, right through the human body, depositing energy in your cells the entire way. Now add the micrometeorites. Because the moon has no atmosphere, there is nothing to burn up incoming debris before it strikes the surface. Everything that Earth would have converted into a harmless streak of light in the night sky reaches the lunar ground at full speed. Most of what falls is tiny grains, smaller than a poppy seed, but these grains are travelling at somewhere between 10 and 70 kilometers per second. At those velocities, a particle the size of a rice grain hits with the kinetic energy of a bullet. A pebble hits with the energy of an artillery shell, and they are constantly falling. Every square meter of the lunar surface, averaged over long timescales, is being sandblasted by a steady rain of high-velocity micrometeoroids. The surface itself is the record of it, an entire crust ground down to powder by billions of years of continuous impact. For an unsuited human being outside, one of these grains through a helmet is instant depressurization and death. For a habitat, the danger is more subtle but no less serious. Any pressure vessel sitting exposed on the lunar surface is being slowly perforated. Sensors, radiators, solar arrays, antennas, the outer skin of every module, all of it is being pitted, cratered, and gradually chewed away by an environment that never stops shooting. A habitat wall thick enough to shrug this off is a wall thick enough to weigh many tons per square meter, which is a wall you cannot easily launch from Earth. Every kilogram sent to the lunar surface currently costs on the order of $1 million. You cannot armor a house that way. And then, worst of all, in the eyes of many engineers who have studied the problem, there is the dust. This is the hazard that gets least attention in popular imagination, and which turned out to be one of the single greatest surprises of the Apollo program. Lunar regolith, the fine grey powder that coats every square meter of the surface, is not like sand or soil on Earth. On Earth, wind and water round off the corners of every mineral grain over millions of years, leaving smooth particles that behave gently when you handle them. On the Moon, there is no wind and no water. Every grain of regolith was made by a hypervelocity impact, either the original impact that shattered a piece of bedrock, or one of the countless later micrometeorite strikes that shattered that piece into smaller and smaller fragments. The result is a powder made almost entirely of jagged, angular, glassy shards, some of them as small as 1/100th of a micrometer. Under a microscope, lunar dust looks like broken glass. Under a microscope, it is broken glass, and that dust gets everywhere. The Apollo astronauts, on missions that lasted only a few days on the surface, came back reporting that lunar dust had become one of the most persistent problems of their entire experience. It clung to their suits by electrostatic charge, because the airless surface builds up static in sunlight, and the grains carry that charge with them. It ground into every hinge, every seal, every zipper, every mating surface. It coated their gloves so thoroughly that after a few hours they could no longer read the checklist sewn onto their wrists. When they climbed back inside the lunar module and removed their helmets, the dust that came in with them made the cabin smell, the astronauts said, like burnt gunpowder. Harrison Schmitt, the geologist on Apollo 17, reported congestion and irritation of his sinuses and eyes, so pronounced that flight surgeons later coined a phrase for it, lunar hay fever. That was after a few days. Now imagine a career. Lunar regolith is roughly 50% silicon dioxide by mass, the same silicate compound that causes silicosis in miners on Earth. Approximately 1 to 2% of it is small enough to be inhaled deep into the lungs, where those jagged glass fragments become lodged and never leave. Long-term inhalation by every model researchers have built would produce something like an accelerated form of the fibrotic lung disease that killed generations of coal miners and quarry workers. On top of that, the dust is chemically reactive in ways we still do not fully understand. Having been bombarded by unfiltered solar wind for billions of years, leaving its surface bristling with what chemists call dangling bonds hungry, unsatisfied chemical sites that grab onto whatever they touch. For a permanent settlement, dust control is not a housekeeping problem. It is a life support problem, and no one has yet demonstrated a system that solves it at scale. Stack these hazards on top of each other, and something becomes clear that Apollo, by the sheer brevity of its missions, was able to hide. The lunar surface is not merely difficult. It is not Antarctica with a longer commute. It is an environment in which every single one of the systems that keep a human being alive on Earth, the air pressure, the temperature buffering, the radiation shielding, the impact protection, the chemical inertness of the local dirt has been stripped away simultaneously. There is no partial solution. You cannot dress warmly and manage. You cannot build a nice log cabin and manage. You cannot rely on the local ecology to help you, because there is no local ecology. Every breath, every degree of body temperature, every unit of radiation dose that you avoid has to be produced by machinery you brought with you, or manufactured after arrival from what is essentially crushed glass. This is the fundamental problem that any serious plan for permanent lunar habitation has to answer, and the answers proposed so far all lead in the same general direction. You could, in principle, build a surface habitat, a pressurized module set down on the plains, connected to solar arrays, life support and communications. The immediate problem is that such a module is transparent to everything the environment throws at it. So the standard proposal is to bury it. Not deeply, but enough. Studies commissioned by NASA and the European Space Agency have consistently found that a covering of roughly 2 to 3 meters of loose regolith piled on top of a habitat module would reduce the radiation dose inside to something approaching acceptable levels for long-duration crews. Regolith is cheap in the sense that it is already there. Move enough of it on top of the roof and you have effectively built a bunker. But regolith is not free either. 2 to 3 meters of loose lunar soil, spread over a habitat with the floor area of a modest apartment, is not a small amount of material. It is tens or hundreds of tons. Every kilogram has to be excavated, transported, and placed by machinery that has to survive the very dust it is shoveling. And the regolith piled on the roof does not solve the temperature problem cleanly. In fact, one study found that adding a regolith cover raised the maximum daytime surface temperature at the top of because the pile itself absorbed and re-radiated solar heat before the underlying layers had a chance to soak it away. Below 30 centimeters, temperature swings drop dramatically. Below about 80 centimeters, the daily cycle disappears almost entirely and the subsurface stabilizes at something near the local yearly average. But getting that shielding into place is an enormous engineering exercise in a place where every construction vehicle is being ground down by the material it is trying to move. And even after you have piled the regolith and buried the habitat and set up the airlocks and managed the dust, you have solved only some of the problems. You still need power through the 14-day lunar night, which means either giant batteries, a small nuclear reactor, or a location like the poles where certain ridges are almost continuously sunlit. You still need communications, which on the near side of the moon means direct line of sight to Earth and on the far side means a chain of relay satellites. You still need to leave the shelter regularly to work, and every departure means suiting up, cycling through an airlock, tracking dust back in, and exposing yourself again to the radiation you spent all that effort shielding against. A buried surface habitat is not a house. It is a fortress on a battlefield that never quiets down. At this point in any serious discussion of long-duration lunar habitation, planners eventually confront the same uncomfortable arithmetic. The moon's surface is so hostile that the amount of engineered shielding needed to make it livable begins to rival, in mass and cost, the habitat you are actually trying to protect. You are, in effect, being asked to transport a small mountain from Earth or to move one on site with machinery that hates its own working environment. And so, in the last 2 decades, a different question has been quietly rising in importance among the scientists and engineers who take the problem seriously. If the surface is this bad, and shielding is this expensive, what if we did not stay on the surface at all? What if the moon has already, over billions of years, done most of the work for us? Because it turns out that the moon has holes in it. Not the craters everyone knows about, those are just dents left by impacts. Holes, actual openings in the surface, some of them tens of meters across, dropping straight down into darkness. They were first spotted clearly by a Japanese spacecraft named Kaguya in the late 2000s, then studied in detail by NASA's Lunar Reconnaissance Orbiter, which has been mapping the moon in exquisite resolution since 2009. There are now more than 200 of these features catalogued across the lunar surface. Some sit in the smooth basaltic plains of the ancient Mare, the dark seas that anyone can see with the naked eye. Others sit in the highlands. They come in a range of sizes, but the most tantalizing ones share a common shape, a roughly circular skylight, walls that plunge vertically or even overhang, and a floor that, in the highest resolution images, appears to extend sideways beneath the surrounding surface. Not a crater, a window into something underneath. For decades, planetary scientists had suspected that such things ought to exist. The Mare are made of frozen lava. When lava flows on Earth in Hawaii, in Iceland, in Sicily, it often does so through tubes, hollow channels formed when the outer skin of a flow cools and hardens, while molten rock continues to drain out from underneath. When the flow ends, the tube is left behind, an empty tunnel running under the ground. Lunar volcanism ended more than 1 billion years ago, but during its long active phase, the same physics should have operated. And on the moon, with only 1/6 of Earth's gravity, the ceilings of such tubes could be far larger and stronger than any lava tube known on Earth. Models suggested they could be tens or even hundreds of meters wide, stretching for kilometers beneath the Mare. The pits, when they were spotted, looked exactly like what you would expect if the ceiling of one of those ancient tubes had collapsed in a single spot, leaving the rest intact. Then, in July of 2024, that suspicion turned into direct evidence. An international team led by researchers at the University of Trento in Italy published a paper in the journal Nature Astronomy analysing radar data collected years earlier by the mini radio frequency instrument aboard the Lunar reconnaissance orbiter. Using new signal processing techniques, they showed that the radar echoes from one specific feature, the Mare Tranquillitatis pit, located roughly 400 kilometers from the site where Apollo 11 had landed, could not be explained by surface geometry alone. There was a void underneath, a cave conduit extending sideways from the base of the pit, tens of meters long and at least several tens of meters wide. For the first time in history, the existence of a subsurface tunnel on another world had been directly demonstrated, and that changes the entire conversation. Because if the Mare Tranquillitatis pit really does lead into an intact lava tube, and if similar tubes lie beneath the 200 other pits scattered across the moon, then humanity's most plausible refuge on this world may not be a shining base on the surface at all. It may be tens of meters of solid volcanic rock overhead. It may be a natural vault, sealed for 1 billion years, waiting in the dark. It may be a way of living on the moon by not living on the moon at all. The catch is that a hole in the ground is not a house, and what happens when you try to turn one into a home is where this story becomes truly strange. The pits were hiding in plain sight. For nearly 40 years after Apollo 11 landed, no one had confirmed that the moon contained openings leading to spaces underneath its surface. The idea had been floating around planetary geology since the 1960s. Apollo-era images of long, sinuous valleys called rills suggested that lava had once flowed in channels across the Mare, and where lava flows on Earth, it sometimes builds tubes, but nobody had proof. There was no photograph of an actual hole in the moon that clearly went somewhere. The lunar surface, at the resolution of the cameras that existed at the time, was a landscape of craters and hills and plains, and every dark spot could be explained as a shadow. There was also a specific reason planetary geologists had long expected such openings to exist. Photographs from the Apollo missions had captured long, winding valleys called sinuous rills, snaking across the surface of several Mare. Some of these rills were narrow and shallow, others were kilometers wide and hundreds of meters deep, and in a handful of cases, the rills appeared to end abruptly. The channel would run for tens of kilometers, then simply stop, as if whatever had been flowing through it had drained into the ground and never come out. On Earth, the same pattern is common in volcanic terrain. Lava tubes that lose their roofs form open channels. Where the roof is still intact, the flow disappears from view and continues underground. If the moon's rills were partly roofed and partly collapsed, the intact sections should still be there, buried and waiting. Nobody could see them from orbit. The cameras were not good enough, but the geology said they had to exist. That changed in 2009. A Japanese spacecraft called Kaguya, formerly known as the Selene mission, had been orbiting the moon since 2007, mapping the surface with a resolution finer than anything that had come before. In one of the images returned to Earth, on the volcanic plain of the Marius Hills region, planetary scientists noticed something odd. It was a dark, roughly circular spot about 65 meters across, tucked into the middle of one of those ancient lava channels. Under most lighting conditions, it looked like a shadow, but when the sun angle was just right, the shadow refused to behave like a crater. Craters cast asymmetric shadows that shift with the sun, revealing their bowl-shaped floors. This did not. The dark spot stayed dark on all sides, at almost every sun angle. The only geometry that fit was a vertical shaft, a skylight, an opening straight down into a void. That single feature, later named the Marius Hills Pit, was the first confirmed lunar skylight in history. It was also a proof of concept. If one existed, others should too. And once astronomers knew what to look for, they started finding them everywhere. The instrument that opened the floodgates was NASA's Lunar Reconnaissance Orbiter, which arrived at the moon in the same year Kaguya spotted the Marius Hills Pit. Equipped with a narrow-angle camera capable of resolving surface features less than a meter across, the orbiter began systematically photographing the entire lunar surface. Its images allowed scientists to search enormous stretches of the moon at high enough resolution to catch a hole only tens of meters wide. Over the next 15 years, that search produced a catalogue of more than 200 confirmed pits scattered across the near and far sides. Most sit inside the smooth basaltic plains of the Mare, but some appear in the older cratered highlands and in the melt sheets of large impact craters. They range in size from about 5 meters across to more than 100 meters. Some are shallow depressions with sloping walls. Others are deep, sharp-edged shafts with walls that plunge vertically, or even overhang, meaning the opening at the top is narrower than the floor at the bottom, a geometry that can only form when something below has collapsed. 3 pits in particular have dominated scientific attention. The Marius Hills pit is the original. Sitting in a region famous for its dense concentration of small volcanoes, it drops about 40 meters to a floor covered in loose rubble and boulders that appear to have fallen in from above. High-resolution images taken at low sun angle reveal that the floor is not a simple flat basin. Portions of it appear to extend sideways into shadowed regions that the camera cannot resolve. Something continues past what the light can see, and in this case, we have more than just images to work with. In 2017, a team of researchers led by scientists at Purdue University in the United States and JAXA in Japan published a reanalysis of data from a different instrument on the Kaguya spacecraft, the Lunar Radar Sounder, a low-frequency radar designed to probe deep beneath the surface. The instrument had recorded reflections from beneath the Marius Hills region that were consistent with a large subsurface void extending for several kilometers, running roughly parallel to one of the sinuous rills that crosses the area. The signal was not conclusive on its own. The radar's resolution left room for interpretation, but combined with the visible pit, the geological context, and gravity data from the same region, it painted a compelling picture. Something long, hollow, and roughly tube-shaped may sit under the Marius Hills, and the visible pit may be the single collapsed skylight into it. If that interpretation is correct, the Marius Hills conduit could be one of the most valuable pieces of real estate in the inner solar system. The second is the Mare Tranquillitatis pit, located inside a rare patch of volcanic plain on the far side of the Moon, in a region called the Sea of Cleverness, one of only a handful of Maria on the side of the Moon that permanently faces away from Earth. This pit is about 100 meters across, larger than the Marius Hills opening, and sits in a geological environment that is not fully understood. Ingenii is unusual because it also contains features called lunar swirls, bright patterns on the surface associated with localized magnetic fields, and because the surrounding terrain is much older than the classic near-side Maria. Whatever process opened the pit into darkness, it did so through a very different piece of the Moon's history. The third, and by far the most famous today, is the Mare Tranquillitatis pit. It sits in the Sea of Tranquility, roughly 400 kilometers from the landing site of Apollo 11, which means Neil Armstrong and Buzz Aldrin walked on the surface, only a short lunar distance from a hole they never knew existed. The pit is about 100 meters across at its widest, and drops approximately 130 meters to a rubble-strewn floor. It is currently the deepest confirmed pit on the Moon, and it has become the single most studied opening on the lunar surface because of what lies underneath it. The discovery that turned Mare Tranquillitatis from an interesting hole into a scientific milestone came in July of 2024. A team led by Leonardo Carrere and Lorenzo Brazzone at the University of Trento, working with colleagues at the University of Padua and other institutions, published a paper in the journal Nature Astronomy. Their achievement was not a new observation, it was a new way of reading an old one. Back in 2010, an instrument on the Lunar Reconnaissance Orbiter called Mini Radio Frequency, a small radar sounder designed to probe just below the lunar surface, had passed over the Mare Tranquillitatis pit and recorded its echoes. At the time, no one had the tools to unpack what the echoes were saying. The Italian team spent years developing a new signal processing pipeline, and when they finally applied it to the archived data, a pattern emerged. Some of the radar reflections from the pit did not come from the pit floor. They came from a cavity extending sideways underneath it, tens of meters beyond the visible opening, at least about 40 meters wide. For the first time in the history of planetary science, the existence of a genuine cave conduit on another world had been directly demonstrated by remote sensing, not inferred from surface morphology, not modelled from analogy, detected. A void exists beneath the Sea of Tranquility, connected to the surface by a shaft that a spacecraft could, in principle, one day fly down. It is worth pausing here and being very careful about what has and has not been shown, because a great deal of popular writing about lunar caves collapses the distinctions in ways that overstate the certainty. Here is what we actually know, in decreasing order of confidence. First, the pits themselves have been directly imaged. More than 200 of them exist as photographs. Their sizes, depths, and floor shapes have been measured to within a few meters. That is a confirmed observation. Second, at least one pit, the Mare Tranquillitatis pit, has now been shown by radar to lead into a subsurface void extending sideways from the base of the shaft. That, too, is a confirmed observation, though the technique is new and the precise dimensions of the cavity carry uncertainty. Third, it is inferred from the geological similarity of many pits to Mare Tranquillitatis that other pits probably also lead into subsurface voids. That is a reasonable inference, but it is not the same as direct evidence. Fourth, it is modelled from theoretical work on lunar volcanism and from gravity data collected by NASA's Gravity Recovery and Interior Laboratory mission, usually called GRAIL, that large lava tube networks may extend for kilometers beneath the Maria, connecting some of the pits into an interlinked system of underground passages. That is a plausible model, backed by supporting data, but no one has ever directly mapped an intact lava tube, extending for more than a few tens of meters. The GRAIL mission itself deserves a moment of description, because its findings underlie much of the current confidence that large voids exist beneath the Maria at all. GRAIL, short for Gravity Recovery and Interior Laboratory, consisted of two identical spacecraft nicknamed Ebb and Flow that orbited the Moon in tandem between 2011 and 2012. By measuring the tiny variations in the distance between the two spacecraft as they responded to the Moon's uneven gravity field, GRAIL produced the highest resolution gravity map of any body in the solar system, including Earth. It could detect density differences beneath the surface at scales of a few tens of kilometers. What it found, in several regions of the Maria, were density anomalies, patches where the underlying rock appeared to be less dense than the surrounding basalt. Some of these anomalies were consistent with buried impact-related features. Others sat in geometries that matched the expected shapes of ancient lava tube systems. In 2015, a team led by Rohan Sood and Loic Chapaz at Purdue University published an analysis suggesting that certain of these anomalies could represent intact lava tubes with cross-sectional widths of up to several kilometers. That is enormous. On Earth, the largest known lava tubes are hundreds of meters across. On the Moon, with its lower gravity, the mechanical arguments say that far larger structures could theoretically support their own roofs. That said, and this is the caveat, that every serious paper on the subject includes GRAIL data, cannot distinguish a single enormous void from many smaller voids grouped together, nor can it prove that any given anomaly represents a hollow rather than simply a region of lower density rock. The gravity signature is consistent with tube networks. It does not require them. Anyone reading a headline that says, "The Moon contains kilometer-wide underground caverns," should mentally translate that into, gravity measurements are consistent with the possibility of such caverns, and if they exist, no one has yet observed them directly. The kilometers-long cave networks that sometimes appear in artist impressions of lunar cities are, at this point in 2026, a hypothesis. They are consistent with what we see. They have not been surveyed. That distinction matters. When engineers begin planning a settlement inside a lunar pit, they are not planning inside a cavern whose walls, ceiling, floor, temperature, chemistry, and structural stability have been characterized. They are planning inside a shape they can guess at from the outside. The Mare Tranquillitatis conduit is the best characterized subsurface feature on the Moon, and even for that one we do not know the height of its ceiling. We do not know the length of its floor, and we do not know how far its walls extend before either continuing into a larger chamber or terminating in a wall of collapsed debris. The Trento team was careful to say so in their paper. Everyone working in the field is careful to say so. It is only when the news filters outward through second-hand reporting that the caves start becoming enormous cathedrals, mapped in perfect three-dimensional detail, ready for construction crews to move in. With that caveat in place, though, the reason these pits matter becomes very clear. Because even a modest cave conduit, even a chamber only tens of meters wide, changes the entire calculation of lunar habitation in ways that no amount of surface engineering can match. It does this by solving, passively, without any human intervention at all, 4 of the 5 worst environmental hazards of the lunar surface at the same time. Consider the radiation first, since that is the hazard for which the arithmetic is starkest. Galactic cosmic rays and solar particle events are stopped by mass. Every centimetre of material between a human body and the sky reduces the dose. On Earth, that mass is provided by roughly 10 metres worth of water-equivalent atmosphere. On the Moon, in a surface habitat, it has to be provided by whatever regolith you can pile on top. As we saw at the surface earlier, 2 to 3 metres of loose lunar soil is enough to knock the dose down to something habitable, and even that requires moving many tons of dirt for every square metre of roof. Now consider what happens beneath a lava tube. The lunar basalt overhead is denser than loose regolith by a factor of roughly 2, around 3 grams per cubic centimetre for solid rock, compared to about 1.5 for the fluffy uppermost layer of soil. And there are not 2 or 3 metres of it, there are tens of metres of it. The Mare Tranquillitatis conduit sits beneath 100 metres or more of solid mare basalt, everywhere except directly under the collapse pit itself. That is enough shielding to reduce the cosmic ray dose to something comparable to what you would experience on the surface of the Earth. Enough that a solar particle event, the sudden burst that could kill a crew caught in the open, would be effectively invisible inside. Enough that a human being could, in principle, live an entire career underneath and never accumulate a dose that would trouble a radiation safety officer. You cannot buy that with hardware. It would take a shielding structure so massive that no realistic launch program could deliver it. The Moon has already put it there. Consider the temperature next. This is where a particularly striking piece of research from 2022 comes in. A study led by Tyler Horvath at the University of California, Los Angeles, using thermal data from the Diviner instrument aboard the Lunar Reconnaissance Orbiter, examined the shaded floors of certain lunar pits, including the Mare Tranquillitatis pit, and reported something remarkable. Instead of following the enormous day-night temperature swing of the surrounding surface, the permanently shadowed regions inside these pits sat at an almost unchanging temperature of roughly 17 degrees Celsius. Room temperature, not comfortable in a colloquial sense, but staggeringly stable compared to the surface just a few dozen meters above, which was ranging over nearly 300 degrees between noon and midnight of the lunar day. The reason is straightforward. Rock is a poor conductor of heat, and lunar regolith is even worse. The surface of the Moon heats and cools rapidly because it is being hit directly by sunlight and then losing that heat to empty space. But even 80 centimeters down, that daily wave has essentially disappeared, damped out by the low thermal conductivity of the soil. At tens of meters of depth, the temperature stabilizes at the long-term average for that region, and inside a permanently shadowed cave conduit, that average is not the equatorial 280-degree swing. It is a quiet, steady value in the neighbourhood of what a comfortable indoor thermostat on Earth might target for a slightly cool office. A settlement inside a lava tube would not need enormous heaters to survive the lunar night, and it would not need punishing radiators to shed heat during the lunar day. It would need only modest thermal control to hold its interior at whatever temperature humans preferred to work in. The Moon, again, has done the hard part. Consider the micrometeorites third. Because rock is opaque to fast-moving particles the way water is opaque to a diving pebble, the moment you are underneath overhead cover, the constant sandblasting stops. Not reduced. Stopped. The chance of a micrometeorite reaching an interior chamber through tens of meters of basalt is, for practical purposes, 0. Every strike is absorbed by the material above. A habitat on the exposed lunar surface is being perforated every day of its operational life. A habitat inside a cave conduit is not. Consider, fourth, the dust. Here the picture is a little more nuanced. Overhead rock does not stop electrostatically charged surface regolith from being tracked in on suits by workers going in and out that will remain a problem no matter where you put the habitat. But the constant deposition of new dust from above, the drift caused by micrometeorite ejecta launching grains ballistically across the surface, the slow accumulation of fresh material on every exposed panel, all of that halts inside a sealed cavity. The interior of a lava tube is one of the few places on the moon where dust does not constantly rain onto every surface. Once you have cleaned a section, it can, in principle, stay clean. That is a small thing compared to radiation. But for a long-duration settlement whose survival depends on solar panels, radiators, seals, and mechanical joints, it is not trivial. Add these four together, and something extraordinary emerges. The lunar surface is dangerous because it exposes everything simultaneously. The interior of a lava tube removes four of those exposures at once, using nothing but the ancient rock that already exists. No hardware, no maintenance, no energy budget. It is, without exaggeration, the single most powerful piece of natural infrastructure anywhere in the inner solar system for a species trying to leave Earth for good. And it has been sitting there, waiting, for well over 1 billion years, which raises the obvious question: if this is so good, why are we not there already? And the answer is where the story sharpens back into difficulty, because natural protection is not the same thing as a natural home. Start with access. The Mare Tranquillitatis pit, like most of the deep skylights, has walls that do not gently slope down to the floor. In many images, they look like the sides of a well. In some parts of the pit, they overhang, meaning that anything descending from the surface would have to swing outward, into empty space, to reach the floor. The drop from the rim to the debris field at the bottom is roughly 100 meters the height of a 30-story building, and that debris field is not level ground. It is a chaotic pile of boulders and shattered basalt, the accumulated wreckage of everything that has fallen or slumped inward since the ceiling of the tube first collapsed. Getting a robot down there is possible with existing rover technology, tethered from above by a cable or lowered by a small crane. Several concept missions have been proposed to do exactly that, but no such mission has yet flown. As of 2026, no human-made object has ever entered a confirmed lunar pit. Every photograph we have of the interior comes from cameras looking straight down from orbit. Then there is the question of what the conduit actually looks like once you're inside. The Trento radar result tells us that a cavity exists and gives us a rough idea of its width, but it does not tell us the height of the ceiling above the tube floor, or the shape of the walls, or the presence of collapsed debris further along the passage, or whether the ceiling is stable or riddled with hairline fractures that might drop chunks of basalt at unpredictable intervals. Lava tubes on Earth, which are the closest available analogues, sometimes contain sections of very stable, arched ceiling that could support enormous loads. They also sometimes contain sections where the ceiling is thin, cracked, or partially collapsed, with rubble piles half filling the passage. Which of these applies to a given point in a lunar tube cannot be determined from orbit. It has to be measured on site. Then there is the question of length. Is the Mare Tranquillitatis conduit a short pocket, extending a few tens of meters beyond the pit and terminating in a rockfall? Or is it a segment of a much longer tube extending kilometers beneath the mare? The radar cannot see far enough to tell. The Grail gravity anomalies discussed earlier hint at large voids beneath some of the Maria, but their resolution is coarse compared to a single tube, and orbital gravity mapping cannot follow a specific conduit along its length. A future dedicated ground-penetrating radar mission, or a rover carrying its own radar into the pit, could resolve the question. That has not happened yet either. Then there is the question of chemistry and contamination. What sits inside a lava tube that has been sealed since the moon's last volcanic era? Probably not much. The interior is a vacuum, cold, dry, and inert. But the surfaces of the walls and floor will be coated with fine regolith that has fallen in during the collapse of the pit, and with dust generated by 3 billion years of thermal cycling and micrometeorite-induced seismic shaking of the ceiling, Some of that dust will have been exposed to solar wind during the collapse event and will carry the same reactive, jagged glass fragment character that Apollo astronauts encountered on the surface. The cave is protected, but it is not clean. And finally, and perhaps most importantly for anyone imagining setting up an inflatable habitat inside a natural chamber and calling it home, there is the question of the pit entrance itself. The overhead protection that makes a lava tube so attractive stops abruptly at the collapse hole. Directly beneath the opening, sunlight falls onto the debris field during the 2-week lunar day, and radiation streams in from the sky. Micrometeorites can still enter through the gap. Anything set up under the pit itself is not sheltered. To take advantage of the natural shielding, you have to move off the debris field into the conduit proper and set up your habitat under overhead rock. That means the natural chamber that everyone finds so appealing is actually an L-shaped space, with the useful part hidden around a corner from the entrance. Getting people, power, air and supplies from the surface, down the pit, across the debris field and into the sheltered section is an engineering exercise all on its own. Every meter of that path has to be built. None of this makes the pits less remarkable. It does not diminish, in any way, the significance of the Trento result or the tremendous natural infrastructure that the Moon has provided. What it does mean is that the pit and conduit system is best understood not as a ready-made home, but as a partially finished building one, where the walls, ceiling, and shielding are already in place, but the entrance, the interior fittings, the utilities, the life support systems, the lighting, the communications, and every square meter of livable floor still have to be constructed and installed by human beings and their machines. The Moon has given the future settlers the hardest part for free. It has given them the shell. It has not given them the house. And that shell has been sitting there in the dark, unwitnessed and unmapped, since long before the first cells appeared in Earth's oceans. The Mare Tranquillitatis conduit was already 1 billion years old when the first fish crawled out of the shallows. The rock overhead has protected its interior from radiation and impact through the entire history of complex life on our planet. And now, in the space of the last 15 years, a handful of orbital cameras and one clever piece of radar signal processing have revealed it to a species that might, sometime in the coming century, become the first thing ever to enter it. The question is what those first entrants would actually do once they were inside. Because a hole in the ground is not a settlement. A settlement is a machine, and it has to be built. Every airlock, every module, every power cable, every water pipe, every ventilation duct, every emergency lift back to the surface has to be designed, transported across 250,000 miles of vacuum, lowered through a 100-meter shaft, and installed by workers wearing the same suits that separate them from a vacuum-driven death by a few millimeters of fabric. The natural shielding solves the environmental problem. It does not solve the engineering problem, and the engineering problem, as it turns out, is where the Moon's second great trick reveals itself. Because the same properties that make the surface so hostile, the dust, the vacuum, the temperature swings, the isolation do not vanish just because you have moved inside. They follow you down. They shape every choice about how the settlement gets built and what it looks like when it is finished, and how the people who live in it spend their days. That is where this story turns next. Standing at the rim of the Mare Tranquillitatis pit, looking down into 100 meters of shadow, is where every abstract discussion of lunar settlement finally meets the hard question. What, physically, do you do next? Because the shielding is free, but everything else, every wall, every wire, every liter of breathable air has to be brought from a planet 250,000 miles away, or made on site from what is essentially crushed volcanic glass. The natural cave is a gift, but it is a gift with no instructions and no interior. And before anyone can even think about turning it into a place a human being could live, the engineers have to answer a question that has been shaping the entire field of lunar architecture for the last 20 years, which is actually the best way to shelter a permanent settlement on the Moon. 3 approaches compete. Each one solves part of the problem and creates new problems of its own, and understanding the trade-offs between them is the only way to see clearly why the natural cave, despite everything, keeps rising to the top of the list. The first approach is the one most people picture when they imagine a moon base: Bring pressurized modules from Earth, land them on the surface, connect them together, and cover the whole thing with piled-up regolith to shield against radiation and micrometeorites. This is the strategy that has dominated NASA concept studies for decades, and that underlies most of the current Artemis program thinking about surface infrastructure at the lunar South Pole. Its virtue is that the modules can be pre-built, tested, and qualified on Earth before they ever leave the launch pad. Its cost is that the shielding has to be moved into place after arrival, and it has to be a lot of shielding. Studies commissioned by both NASA and the European Space Agency have consistently found that a covering of roughly 2 to 3 meters of loose regolith is the minimum needed to reduce the interior radiation dose to something acceptable for a career-length stay. 2 to 3 meters. Over the footprint of even a small habitat, that is on the order of 100 tons of dirt that has to be excavated, transported, and piled up by machinery working in vacuum, inside a temperature range that can swing across nearly 300 degrees in a fortnight, and inside a dust environment that is actively trying to destroy every moving part. The second approach removes the shielding problem by burying the habitat outright, digging a pit, lowering the modules into it, and backfilling from above. The advantage is that the shielding is thicker and more evenly distributed. The disadvantage is that lunar excavation is one of the most difficult engineering problems anyone has proposed for the 21st century. Regolith is not soil. It is a densely packed, cohesive, glass shard-rich mixture that has been compacted by billions of years of micrometeorite impacts. In some places, its density approaches that of soft rock. Any excavator working through it has to grind, cut, or blast, all of which produce clouds of the same jagged airborne dust that Apollo astronauts found so destructive, all of which have to be managed in vacuum, and all of which chew through metal tools with astonishing speed. A single lunar excavation project on the scale needed to bury even a small habitat would probably consume more machinery, more spare parts, and more crew hours than the entire Apollo program combined. The third approach, the one that keeps rising in importance the more the numbers are examined, is to use what the Moon has already built. Find a natural cavity, lower the habitat modules into it through an existing skylight, set them up under the overhead rock, let the ancient volcanic ceiling do the shielding work that would otherwise have required moving a small mountain. The advantage in transported and manufactured mass is enormous. A team of researchers at the Colorado School of Mines calculated in one study that using a lava tube instead of piled regolith could reduce the total shielding-related construction mass at the site by more than an order of magnitude, depending on the size of the settlement. That is the difference between a project that requires dozens of heavy lift launches and one that requires only a handful. But the trade-off, as the pit geometry already hinted, is access. A surface habitat can be reached by driving a rover up to its front airlock. A buried habitat can be reached through a purpose-built stair or elevator installed as part of the construction. A lava tube habitat has to be reached by descending 100 meters of vertical shaft, crossing a chaotic debris field, and traveling however far around the corner of the L-shaped conduit before you reach the sheltered section. Every gram of cargo, every crew member, every piece of construction equipment, every replacement part, every rescue team, and every evacuation route has to go through that same single narrow opening. In the language of civil engineering, a lava tube settlement is a single point of access facility, and single points of access, on Earth, are what building codes are specifically designed to prevent. Which means that the very first piece of infrastructure any serious cave settlement would require, before a single habitat module could even be lowered inside, is a way to get things down the pit safely. And this is where the actual construction sequence has to begin. The current mainstream engineering thinking, drawn from concept studies by NASA's Jet Propulsion Laboratory, the European Space Agency, and academic groups at institutions like the University of Arizona and the Colorado School of Mines, imagines the sequence unfolding across several successive robotic missions before any human crew is committed to the site. The first mission is reconnaissance. A rover, dropped near the rim of the pit, would deploy a tethered probe or a small hopping drone to descend into the shaft and map the interior in detail. The technique has already been demonstrated in prototype form on Earth. The European Space Agency ran a concept study called Daedalus, a spherical rover the size of a beach ball, carrying LiDAR, cameras, and radar, designed to be lowered on a cable into a pit and then rolled across the debris field. NASA's Jet Propulsion Laboratory has proposed a similar concept called Moondiver. Neither has flown. Neither is currently funded to fly, but both represent the kind of mission that has to happen first, because until a robot has been inside a specific pit and measured the geometry of its interior, no one can plausibly design a habitat to fit. Once the interior has been mapped and the length, height, and structural stability of the conduit have been at least partially characterized, the second phase begins. Access infrastructure has to be installed. Somewhere along the pit rim, engineers have to build a permanent transport system capable of moving people and cargo between the surface and the cave floor. Several concepts have been proposed. The simplest is a heavy-duty cable elevator, essentially a version of the systems used on Earth to lower workers into deep mines, adapted for a vacuum environment and 1/6 gravity. A more ambitious version uses a permanent ramp cut or built into one wall of the pit, allowing wheeled vehicles to drive directly down. The most expensive but most redundant version installs multiple independent access systems from the start, so that a failure of anyone does not trap the settlement below with no way out. Whichever version is chosen, it has to be built before any human crew arrives, because the crew cannot install its own escape route while relying on it. The third phase is habitat delivery. Modules, likely a mix of rigid metal shell components and expandable inflatable ones, are landed on the surface near the pit, driven to the rim, and lowered through the shaft to the cave floor. Rigid modules provide known volumes and predictable structural performance. Inflatables, of the kind that Bigelow Aerospace and now Sierra Space have been developing for orbital use, provide much more habitable volume per kilogram of launch mass, which is critical when every kilogram costs a fortune to deliver. The current baseline in most academic studies is a hybrid, a spine of rigid modules containing life support, power, and airlocks, connected by inflatable soft-shell sections providing living quarters, laboratories, and agricultural bays. Inside a cave, an inflatable makes especially good sense, because the overhead rock is doing the shielding work that on the surface would have required the shell to be much thicker. Under 100 meters of basalt, the module skin only has to hold air. It does not have to stop radiation. The fourth phase is site preparation inside the conduit. The debris field on the cave floor has to be cleared or graded flat enough for the modules to sit on. That clearing operation is itself a substantial engineering exercise. The debris field at the bottom of a pit like Mare Tranquillitatis is not gravel. It is a chaotic pile of basalt boulders ranging from small cobbles to blocks the size of shipping containers, tumbled together over billions of years as pieces of the collapsing ceiling fell and pieces of the pit walls slumped inward. Some of the blocks are stable, some are precariously balanced, some are wedged against neighbours in ways that will hold indefinitely, and some are one small vibration away from rolling. Robotic construction machines will have to sort this field, moving the largest blocks to the sides of the chamber, breaking up medium-sized ones with rock hammers or chemical cutters, and grading the resulting rubble into a level working surface. On Earth, this kind of work is done by heavy construction equipment weighing tens of tons and drawing hundreds of kilowatts of power. On the Moon, the equivalent machines will be smaller, lighter, and running on power delivered by cable from the surface. They will work in 1/6 gravity, which changes both what they can lift and how the debris they are moving behaves once released. A boulder tipped over on the Moon does not fall the way it does on Earth. It drifts slowly, keeps its rotational momentum, and lands with less crushing force. That is helpful in some ways. The machines do not need to be as strong and dangerous in others, because a slowly tipping block gives a nearby robot plenty of time to be knocked off balance if it is in the wrong position. None of these machines exist yet in flight-ready form. Several prototype lunar construction rovers have been demonstrated in laboratory settings on Earth, including designs from NASA's Jet Propulsion Laboratory, from academic teams at institutions like the Colorado School of Mines, and from commercial partners in the private space sector. Each demonstrates part of the problem: excavation, grading, autonomous navigation on rough terrain, or robotic manipulation of large objects. None of them combines all of the required capabilities in a package that has been tested in real lunar gravity, real lunar dust, and real lunar vacuum. The first pit floor construction operation, whenever it happens, will be the largest single robotics test ever attempted beyond Earth orbit. The cavity walls need to be inspected for loose material that might one day fall onto the habitat. In some concepts, the modules are placed inside a protective outer shell, a semi-rigid enclosure that provides a second pressure barrier and a smoother interior for people to work in. In others, the modules sit directly on the cave floor, connected by flexible tunnels. Either way, the internal geometry of the settlement has to be built around the shape of the natural chamber, which means every settlement is bespoke. Nothing is standardized. Each pit demands its own architecture. Then comes the fifth and most complicated phase, connection. Power, air, water, communications, thermal control, every one of these systems has to be run from the surface, down the shaft, across the debris field, and into the modules. Consider power first. The moon's 14-day night makes solar power alone insufficient for a permanent settlement anywhere except a handful of ridges at the poles that receive nearly continuous sunlight. Even at those locations, the shadowed periods can last long enough that some form of storage or backup is needed. For a settlement in the low-latitude Mare, which is where most of the pits sit, including Mare Tranquillitatis, solar power for 2 weeks, followed by darkness for 2 weeks, is not a workable baseline, which is why almost every serious concept for a permanent lava tube settlement includes some form of nuclear power. NASA's Fission Surface Power Project, developed jointly with the United States Department of Energy, has spent the last several years advancing a class of small fission reactors designed specifically for lunar and eventually Martian use. In 2022, NASA awarded contracts to 3 industrial teams, one led by Lockheed Martin, one by Westinghouse, and one by a smaller company called IX, to develop preliminary designs for a reactor capable of delivering roughly 40 kilowatts of electrical power continuously for at least a decade on the lunar surface. 40 kilowatts is not enormous by terrestrial standards. It is roughly the power draw of a small hotel, but for a lunar settlement that has already stripped its systems down to the minimum viable configuration, it is a lifeline. The reactors themselves are small enough to fit on a single lander. In most current designs, the reactor core sits inside a shielded housing on the surface, connected to a heat rejection system that radiates waste heat into the vacuum through large panels and to a power conditioning unit that converts the reactor's output into electricity at a voltage the habitat can use. Cables then run from the surface installation down the shaft, across the debris field, and into the habitat modules. The reactor does not care about the 14-day night. It does not care about temperature extremes. It runs on its own schedule, delivering steady power around the clock, for years, using enriched uranium fuel that came from Earth in a single shipment, and will not need to be replenished for the reactor's operational lifetime. The refueling problem, when it eventually comes, is genuinely difficult. Nobody has yet worked out a practical procedure for changing the fuel in a reactor located on the surface of another world, and current concepts assume that at end of life the reactor will simply be shut down and a new reactor delivered on a fresh lander to replace it. That means every long-term settlement plan implicitly commits to a slow but continuous stream of nuclear payload launches from Earth over the coming decades. It also raises regulatory questions that no spacefaring nation has yet had to answer at scale: how to license, insure, and manage the eventual disposal of nuclear hardware on another body. Those questions are being worked on. They are not solved. That steady output still depends, however, on a machine sitting exposed on the lunar surface, being sandblasted by micrometeorites, thermally cycled by the day-night swing, and slowly coated with electrostatically charged dust. The very qualities that make the reactor an ideal power source for an underground settlement, its independence from sunlight, its long fuel life, do not exempt it from the environment overhead. The reactor will need servicing. The servicing will be done by robots. The robots will need spare parts. Every layer of the system rests on the layer beneath it, and every layer has to keep working. Cables running down a 100-meter shaft are also cables that can be cut, damaged, or degraded, which means redundancy. 2 independent power feeds from 2 separate reactors. backup batteries inside the cave sized to carry the settlement through hours or days of complete power loss, emergency systems that can be triggered from anywhere in the settlement without waiting for confirmation from the surface. Every one of these redundancies costs mass. Every kilogram of mass has to be launched from Earth, and every launch is a new opportunity for something to fail before it ever reaches the site. Air is similarly demanding. A closed-loop life support system inside a cave settlement has to do everything a spacecraft life support system does: scrubbing carbon dioxide, generating oxygen, controlling humidity, filtering particulates, managing trace contaminants, but at a scale much larger than any spacecraft has ever attempted, and for a duration measured in years rather than months. The International Space Station provides the current state-of-the-art. Its life support system recycles roughly 90% of water and about half of the oxygen. Even at that efficiency, resupply is constant. A lunar cave settlement, resupplied at best every few months and possibly at best once a year, needs to close its loops much further. 95%, 98%, ideally beyond. No such system has ever been demonstrated at habitat scale for the required duration. Every existing test has revealed some new failure mode, a subtle contaminant, a bacterial bloom, an unexpected consumption of a filter medium, and each of those failures, in a settlement whose nearest resupply is 3 days away in a functioning rocket, becomes a genuine threat to survival. Then there is water. If the settlement is at low latitude, near the Mare where most of the pits are, there is no accessible water ice nearby. The polar deposits, where more than 600 billion kilograms of ice may exist in permanently shadowed craters based on data from the Lunar Crater Observation and Sensing Satellite and other missions, are thousands of kilometers away from Mare Tranquillitatis. The settlement either has to import water from Earth, extract it from oxygen and hydrogen, imported separately, or, in the longer term, ship it in from the polar regions using surface transport that itself has to be built. Every option is expensive. Every option adds to the growing list of things that have to work in perfect coordination for the settlement to keep functioning day after day. Now consider a hazard that has quietly been building beneath every step of this story: the dust. The regolith problem that made the surface so hostile does not vanish once you go underground. It moves. Every rover coming down the shaft carries dust into the cave. Every construction operation kicks up new dust from the debris field. Every airlock cycle, no matter how carefully designed, transports some of that dust from the exterior into the pressurized interior. And once dust is inside, in 1/6 gravity, it does not settle out of the air quickly. It hangs, it drifts, it clings to surfaces by electrostatic attraction, coats, filters, works its way into bearings, and grinds down every mating surface it touches. NASA's Dust Mitigation Working Group has been studying this problem for more than a decade. There is no elegant solution. There are only strategies: magnetic filters, electrostatic curtains, multi-stage airlocks with progressively cleaner intermediate chambers, dedicated changing rooms, where suits are hosed down and stored outside the main habitat volume, and each strategy adds cost, mass, and complexity. Every kilogram of dust mitigation hardware is a kilogram that has to come from somewhere. The dust problem interacts especially cruelly with the lava tube approach because the natural cave, sealed for 1 billion years, contains its own resident dust load, the material that has fallen in during the pit collapse, and the material generated by billions of years of thermal cycling and micrometeorite-induced shaking of the ceiling above. That interior dust is chemically similar to surface regolith, with the same jagged shard morphology, the same silicate composition, and the same reactive dangling bonds where the mineral surfaces meet the vacuum. Any construction activity inside the conduit driving on the floor, drilling anchor bolts into the walls, moving modules across the debris field, will kick that dust into the vacuum, where in 1/6 gravity it will hang in a slow drifting cloud for hours. Workers in suits will breathe filtered air, but the dust will settle on every surface they leave behind, including the surfaces of the modules being installed. Some of that settled dust will be tracked into the habitat when the airlocks first cycle. Some of it will be there for years. Communications adds another layer. On the near side of the Moon, direct radio contact with Earth is possible from the surface anywhere the Earth is above the horizon, which for most near-side locations is nearly all the time. Inside a cave, direct contact is impossible. Radio waves do not pass through 100 meters of basalt any more than sunlight does. Every message between the underground settlement and Earth has to be routed through a surface relay. That relay has to be powered, protected from the same environmental hazards as everything else on the surface, maintained by robotic servicing missions, and duplicated for redundancy, because if the single relay antenna fails, the settlement is cut off. Similarly, any surface exploration by the crew, once they have suited up and taken the elevator to the top, requires either direct line of sight to a relay on the pit rim or a chain of small relays extending across the terrain they intend to visit. There is no equivalent of a mobile phone network. Every square kilometre of surface communication coverage has to be built. And then there is navigation. The global positioning system does not exist at the Moon. There is no continuous satellite constellation providing precise position fixes to anyone standing on the lunar surface, let alone to anyone standing inside a cave where the sky is not even visible. NASA has proposed a system called LunarNet, and the European Space Agency has a similar initiative called Moonlight, aimed at eventually providing navigation and communication services around the Moon. Neither is fully operational as of 2026. Both are in early implementation phases. Until they exist, every rover, every suited worker, every drone, every piece of construction equipment on the lunar surface has to navigate by dead reckoning, visual landmarks, or short-range radio triangulation from local beacons. Inside a cave, even those local beacons have to be installed and maintained by hand. There are no natural landmarks in a chamber that no one has ever seen. There is no view of the sky to reset your position by. If your inertial navigation drifts, you are lost inside a completely dark room the size of a large warehouse, wearing a suit that will run out of air in a few hours. Which brings the discussion to the single most frightening word in the entire vocabulary of underground lunar habitation: evacuation. Every terrestrial building code, every mining safety regulation, every submarine design standard is built around the principle that people trapped in a hostile environment need multiple independent ways out. The lava tube settlement, in its baseline design, has one shaft, one elevator or ramp system, one route to the surface. If any of the following happens, the elevator jams. The ramp is blocked by a rockfall inside the pit. The debris field between the cave and the shaft becomes impassable due to a subsidence event, or a dust storm at the surface temporarily disables the machinery at the top. The settlement below is sealed in, and it stays sealed in until the problem is fixed. Rescue from Earth is 3 days away at the fastest, and that rescue mission cannot descend into the pit if the access infrastructure is already broken. The engineering response to this is to build multiple access points, but that requires either drilling additional shafts through the ceiling from the surface, a construction project of terrifying complexity, or discovering a second natural pit connected to the same lava tube system, which as of today has not been done for any of the confirmed pits. Some concept studies imagine future settlements built along tubes with multiple skylights, allowing entry and exit at several points. Whether such tubes exist, and whether their multiple skylights connect to the same underground volume, is a question that will not be answered until dedicated missions have flown and mapped the interior of at least one system in detail. Until then, every proposed cave settlement is a facility with a single door, and everyone inside has to trust that the door will keep working. There is one more layer of the engineering problem that has to be addressed before the physical settlement is complete, and it is a subtle one: structural stability. The Mare Tranquillitatis conduit has been sitting quietly under its ceiling for something like 3 billion years. There is no reason to think it will suddenly collapse in the next century, but there is also no reason to think it is uniformly stable everywhere along its length. Lunar seismology, based on data collected by seismometers left behind by the Apollo missions, tells us that the Moon experiences small tremors called moonquakes, driven partly by tidal stress from Earth's gravity and partly by thermal expansion and contraction of the crust across the fortnightly day-night cycle. Most of these quakes are gentle. Some, particularly the shallow moonquakes that appear to originate within the upper crust, can be surprisingly strong magnitudes of 5 or higher on the Richter scale, capable of causing structural damage if a building on the surface were unlucky enough to sit near the epicenter. Inside a cave, a moderate moonquake could dislodge loose material from the ceiling. It could shift the debris field. It could damage anchor points holding cables and utilities in place. Any settlement inside a natural conduit has to be designed with the assumption that the interior may occasionally rearrange itself, and that periodic rockfall from the ceiling is not a hypothetical worry, but a design constraint. And this is what turns the natural cave, so appealing at first sight, into something more complicated than a shelter. It is a shelter. It solves problems that would otherwise be almost unsolvable, but it demands an engineering commitment of extraordinary depth in order to be turned into a functioning settlement. Everything about it, the access shaft, the vertical transport system, the modules, the power, the air, the water, the thermal control, the communications, the navigation, the dust mitigation, the seismic monitoring, the emergency escape systems has to be designed, delivered, and installed before a single crew member can move in for good. And every piece of that infrastructure is a piece that can fail. In an environment where failure has consequences no terrestrial construction project has ever had to contemplate. There is a phrase that comes up repeatedly in the technical literature on lunar habitation, sometimes explicitly and sometimes only by implication. The phrase is defense in depth. It comes from the safety analysis of nuclear reactors, where the operating principle is that no single barrier between hazard and human should be assumed reliable. Every critical function must be protected by multiple independent layers, so that failure of any one layer still leaves the system safe. On the lunar surface, defense in depth means multiple pressure barriers, multiple oxygen systems, multiple power sources, multiple communication paths, and multiple escape routes, all working in coordination. Inside a lava tube, defense in depth means all of the above plus additional layers to compensate for the single access point, the potential for rockfall, and the impossibility of quick rescue. Nobody has ever built a facility on Earth that had to meet this standard for years on end with no external support. The closest analogues are nuclear submarines, deep-sea research stations, and Antarctic winter-over bases, and each of those falls short in specific ways that matter. Submarines can surface, deep-sea stations can be evacuated to a support ship, Antarctic bases can be resupplied by aircraft when the weather permits. A lunar cave settlement has none of these fallback options. If something goes wrong, the people inside are alone with the problem for as long as it takes to fix it or to survive it, none of which is a reason not to try. It is a reason to be honest about what trying means. A permanent lunar settlement inside a lava tube is not a village in a picturesque cavern. It is a small industrial facility packed with machinery, connected to the surface by a single lifeline, protected from a hostile universe by a thin metal skin and a ceiling of ancient rock. It is a structure whose survival depends on every one of its systems working every day, in an environment where the only backup for a broken system is another system that was designed at the same time by the same people and shipped to the site on the same rockets. And this is the settlement people are going to have to live inside, not for a mission, not for a rotation, for years, for careers, perhaps in time for generations. What that experience actually feels like, waking up under artificial light, exercising against a gravity that quietly weakens the skeleton, breathing recycled air that has been through the same lungs for months, working shifts in a dust-choked airlock, going months without seeing an unfiltered horizon, is where the story becomes something more than an engineering problem. It becomes a question of what it means to be human inside a place that was never built for people. That is where this story now turns. The alarm is not a sound, it is a light. A soft, warm-toned band of full-spectrum LEDs set into the ceiling of the sleeping cubicle, tuned across half an hour to imitate the colour of a slow terrestrial sunrise. There is no window because there is nothing outside a window that would be worth looking at. Beyond the fabric wall of the cubicle is the interior of an inflatable habitat module. Beyond the module is the floor of a lava tube. Beyond the tube ceiling is 100 meters of ancient basalt. Beyond the basalt is the surface of the moon, currently in the middle of its 14-day night, where the temperature is somewhere near minus 170 degrees Celsius, and nobody has been outside for a week. The resident sits up in 1/6 gravity, and for a moment feels the small, permanent wrongness of it, the way the body drifts a little farther on every motion, the way the pillow does not stay quite where it was put, and then, as every morning, ignores it and gets on with the day. This is the part of the story that is easiest to get wrong. Not because the physical facts are unclear, but because our imagination keeps trying to make it look like a science fiction poster. A vast, softly lit cavern, ferns growing along the walls, a skylight glowing above, families walking together across a plaza. That image is not what an underground lunar settlement will look like, and it is not what living in one will feel like. The cavern, if there is one, will be dark. Most of its volume will be unused. The modules will occupy only a small footprint on the cave floor. The interior of the module will resemble a cross between a submarine, a laboratory, and a very small greenhouse. And the psychological texture of daily life inside it will bear no resemblance to any environment human beings have evolved to occupy. Consider first the light. The lunar surface, in daytime, is bathed in unfiltered sunlight roughly 1 1/3 times as intense as at Earth's surface. None of that light reaches the cave floor. The only illumination inside the settlement, at every hour of every day of every month, comes from artificial sources, LEDs, mostly, chosen for efficiency and tuned in color temperature to imitate the changing shades of a terrestrial day. Morning is warm, midday is blue-white, evening slides towards amber, night, in the sleeping areas, drops to a dim red. The residents can, if they choose, keep the settlement on Earth time a 24-hour cycle disconnected from the actual movement of the sun overhead. Most concept studies assume they will, because circadian biology does not adapt gracefully to any other rhythm. Human beings evolved to run on a roughly 24-hour clock, and the moment the light cues do not match, sleep quality deteriorates, mood destabilizes, and cognitive performance falls. The lunar day is 29.5 Earth days long. Nobody is going to live on it. Instead, the settlement runs on an artificial cycle that has nothing to do with the sky outside. This has consequences that only reveal themselves over months and years. The residents will never see sunlight directly, on their skin, without a suit and a helmet between them and the sky. Vitamin D production, which in humans depends on ultraviolet exposure of the skin, will not happen naturally. It has to be supplemented either through dietary intake or through carefully controlled ultraviolet lamps in specific areas of the settlement, and both options require ongoing medical monitoring to catch deficiencies before they become a problem. Long-duration crews on the International Space Station already have to manage this with dietary supplements, since even the cupola windows block the ultraviolet wavelengths that skin needs to produce vitamin D naturally. A cave resident will not see the Terminator at all unless they suit up and take the elevator to the surface, which, for reasons we will come to, they will not do often. Now consider gravity. The Moon's gravity is roughly 1/6 of Earth's. This is famously well known, and equally famously misunderstood. The popular image, drawn from the bounding walks of the Apollo astronauts, is that lunar gravity is somehow fun, a lightness that makes ordinary motion effortless. What that image leaves out is that Apollo astronauts spent, at most, a few days on the surface. They were not there long enough to be harmed by the gravity itself. They were harmed, if at all, by the flights that got them there and back. The microgravity of the transit stages caused measurable changes in their bone density, muscle mass, and cardiovascular function before they even arrived. Nobody knows what happens to a human body that lives permanently in 1/6 gravity. Nobody has ever done it. Every scrap of data we have about partial gravity is either extrapolated from microgravity studies aboard the space station, or extrapolated from bed rest studies on Earth, or extrapolated from short-duration animal experiments. The extrapolations broadly suggest that 1/6 gravity is not enough to preserve normal bone density, muscle strength, or cardiovascular tone over years of exposure. Astronauts on the space station, in essentially zero gravity, lose roughly 1% of their bone mineral density per month in weight-bearing bones, despite spending 2 hours a day on specialized resistive exercise machines. In 1/6 gravity, the loss should be slower but not zero, and quite possibly still fast enough that a career-length stay on the Moon leaves permanent effects. Vision changes. Cardiovascular deconditioning. Immune system disruption. The full syndrome may resemble a slow, mild version of what long-duration space station crews experience, but no one has ever measured it in the real environment, because the real environment does not yet contain anyone measuring it. So every resident of the underground settlement exercises, not as a preference, but as a medical prescription. 2 hours a day, minimum, on a combination of resistive machines that force the muscles and skeleton to work against loads they would otherwise never experience. A treadmill in 1/6 gravity is useless for cardiovascular conditioning unless the runner is strapped down by shoulder harnesses that pull them against the belt with something approaching their earth weight. Weightlifting stations use vacuum cylinders or magnetic resistance because free weights would be far too light. The daily exercise slot is not optional. Missing it, repeatedly, produces measurable declines in bone density within weeks. The medical officer of the settlement, whoever they are, will spend a significant fraction of their time managing the physiological consequences of an environment that the human body was never designed for. Now consider the air. The inside of the habitat is pressurized. Most concept studies use roughly Earth-normal atmospheric pressure, or a slightly reduced pressure with elevated oxygen content to reduce structural loads on the module skin. The air is recycled. Every breath a resident takes has been through their lungs, or someone else's, before. Carbon dioxide is stripped by scrubbers. Oxygen is regenerated by a combination of electrolysis units, splitting water, and in the longer-term concepts, bioregenerative systems, using plants or algae to close part of the loop. Humidity is managed, trace contaminants are filtered, and every one of these systems is running 24 hours a day in the background of daily life. When they work, nobody notices them. When they fail, everybody does. A carbon dioxide scrubber that stops working produces symptoms within hours. Headaches, drowsiness, impaired judgment, long before the residents themselves realize anything is wrong. Modern habitat concepts include multiple independent monitoring systems, alarms, and backup scrubbers. But the point remains, the atmosphere inside the settlement is a machine. It is not a place. It exists only because a set of pumps, filters, and reactors are running continuously, and if they stop, so does everything else. Water follows the same pattern. Every litre of water in the settlement has been drunk, sweated, or urinated by someone before. The processing systems are more advanced than anything currently flying, but the principle is the same as on the space station. Urine goes into a distillation system, which recovers about 90% of the water in it. Humidity condensed from cabin air goes into a filtration stack. Wastewater from hygiene is treated and recycled. Fresh water arrives only in the small trickle imported from Earth or extracted from local ice, and the loss rate through venting, through leaks, through consumption in chemical reactions has to be balanced by that trickle over months. A resident who has been in the settlement for a year has drunk their own urine, filtered and purified hundreds of times. This is not a shocking fact once you have thought about it for a few seconds. It is simply the physical reality of a closed-loop life support system. On Earth, we do the same thing. The water in a glass has been through the digestive tracts of countless animals over the geological history of the planet. But Earth has an entire hydrosphere, an entire biosphere, doing the recycling for us. In the settlement, a set of stainless steel canisters does it, and the canisters have to work. Food is the same story with an extra layer of complexity. Some food is imported from Earth freeze-dried, shelf-stable, packaged for years of storage. It is nutritionally complete, but psychologically flat. Most concept studies for permanent lunar habitation assume that a significant fraction of the settlement's food supply will be grown on-site, in dedicated agricultural bays lit by LED grow lights and cultivated in soilless hydroponic or aeroponic systems. Leafy greens are the easiest. Lettuce, kale, spinach, herbs, tomatoes, peppers, and strawberries have all been grown successfully in space experiments. Staple crops like wheat, rice, and potatoes are more difficult, requiring more area, more energy, and more processing infrastructure. Meat and dairy are, for the foreseeable future, either imported or absent. Some longer-term studies imagine insect protein, mealworms, and crickets are efficient at converting plant matter into edible protein, and have been proposed for space food systems for decades. But human resistance to eating insects in visible form remains a factor, and the technology to grind them into palatable protein powders is still developing. The agricultural bay is one of the few places in the settlement where a resident can experience something like the presence of another living thing. Everything else is machinery. The plants, imperfect and slow-growing, are alive. Studies of both isolated Antarctic winter over cruise and the small biosphere-in-a-box experiments run in the 1990s have consistently found that human beings placed in artificial environments derive disproportionate psychological benefit from access to living plants, not just for the food, for the visible evidence that something other than a pump or a fan is participating in the settlement's daily life. Concept studies include agricultural bays. Partly for this reason, the math on their calorie output is often marginal. Their contribution to morale is not. Now consider the space. The interior volume of an entire lunar settlement, at least in the first several decades of any realistic concept, will be small. A crew of 8 to 12 people, perhaps 4 or 5 connected modules, each the size of a large shipping container. Total pressurized volume comparable to a modest single-family house on Earth, but shared among the entire crew and containing not just living quarters but also laboratories, workshops, agricultural bays, medical facilities, storage, and life support equipment. Private space is minimal. Each resident probably has a sleeping cubicle roughly the size of a compact car interior, containing a bed, a small workstation, a personal storage locker, and perhaps a screen. Everything else is shared. Meals are eaten together. Exercise is done in a shared bay. Hygiene facilities are timed and rotated. Communications with Earth are private but bandwidth limited, and every message is archived for engineering review. The psychological literature on confined populations, Antarctic stations, submarines, offshore oil platforms, orbital space stations is remarkably consistent about what happens next. In the first weeks, novelty carries people through. In the first months, routines settle in and productivity is high. Then, somewhere around the 3 to 6 month mark, a phenomenon that researchers call the third quarter effect begins to appear. Small conflicts between crew members become larger. Minor irritations become chronic complaints. Cognitive performance dips. Motivation flags. This is not a failure of the individuals involved. It is a predictable feature of the environment, observed across every long-duration confinement study ever conducted. Trained, screened, motivated professionals are not immune. The best designed missions manage the effect through careful crew selection, scheduled communications with families, rotating leadership responsibilities, and access to whatever variety and privacy the environment allows. In an underground lunar settlement, the environment allows very little, because the sky is not there. And this is where the story of the settlement, patient and technical up to this point, has to become honest about something harder to measure. The residents do not see the sky, not directly, not from inside the settlement, not for weeks at a time. If they want to see the moon's surface, they suit up, cycle through an airlock, take the elevator to the pit rim, and step out into an environment where every safe minute is bought with the continuing performance of a machine strapped to their back. Even then, they see only the local geography, a grey plain, a black sky, the sun as an unfiltered white disk, and the Earth, if they happen to be on the near side, hanging fixed at whatever angle above the horizon their landing site permits. The Earth does not rise or set for a lunar surface observer. It sits, blue and unchanging, in the same spot in the sky, day and night, month after month. It is beautiful. It is also, in a way that is difficult to convey until you have thought about it for a while, unnerving. Every image of home, every reminder of where you came from, is fixed in one place and cannot be avoided or approached. It is simply there, forever. And the trips to the surface will not be frequent. Every excursion is a radiation dose. Every excursion is a dust exposure. Every excursion requires suit up, checklist, buddy check, airlock cycling, and in the event of a solar particle event, warning an immediate scramble back inside. The settlement's medical officer will track surface time carefully and residents will not be permitted to accumulate more than a strictly limited number of hours per year. Most residents, most of the time, will not be outside. They will be inside, under the rock, in the same set of rooms they were in yesterday and will be in tomorrow. This is the shape of the life. Waking under artificial light, exercising against a gravity that is quietly reshaping the body, breathing air that has been through everyone's lungs, drinking water that has been through everyone's kidneys, eating food grown in racks under lamps, working in a small volume with the same small group of people, speaking to Earth across a delay of just over 1 second, short enough for conversation, long enough to feel it every time, waiting for the resupply that arrives every few months, carrying letters, small gifts, replacement parts, and the occasional new crew member coming out to join the settlement, or the returning crew member finally going home, never feeling wind, never feeling rain, never smelling anything that has not been carried up from Earth or grown in the agricultural bay, never standing outside without a suit, never, in the ordinary sense of the word, going anywhere. To make what this feels like more concrete, follow a resident through one specific day, the day, perhaps once a month, when they are scheduled to leave the settlement and go to the surface. The morning begins the same as any other. Artificial sunrise, breakfast in the shared galley, a quiet review of the day's schedule on a handheld screen. But today, the schedule includes a surface excursion, which means that from the moment the resident finishes eating, the pace of the day changes. Every step is proceduralized. Every step has a checklist. Every step is verified by another human being before proceeding. The first stop is medical. The settlement's medical officer takes a set of baseline measurements: blood pressure, heart rate, blood oxygenation, hydration status, and reviews the resident's cumulative radiation exposure log. If the resident is close to their annual limit, the excursion is cancelled. If they are within their allowance, they are cleared. The clearance is not a formality. Every additional hour on the surface is measured against a career total that determines how long the resident can safely remain part of the settlement. Nobody gets extra hours. Nobody is exempt. The second stop is the pre-breathe protocol. If the habitat runs at reduced pressure with elevated oxygen, a common design choice, because lower pressure means thinner walls and less mass to launch, the resident is already partially acclimated. If it runs at full earth pressure, they will spend an hour or more breathing pure oxygen through a mask, purging nitrogen from their blood, so that when they enter the lower pressure of the suit, they do not develop the same decompression sickness that afflicts scuba divers who ascend too fast. The pre-breathe is boring. It is also non-negotiable. The third stop is suit up. The resident walks to the airlock, where their personal suit is docked to the suit port on the outer wall. They climb into it through the back hatch, one leg at a time, sealing the hatch behind them and beginning the pressurization cycle. As the suit inflates around them, they run through the checklist: helmet seal, communications check, biometric telemetry, water supply, oxygen supply, carbon dioxide scrubber, cooling loop, radiation dosimeter, emergency beacon. Each item is confirmed by another resident watching from the interior. Only when every item is green does the suit undock from the habitat and the residents step away from the wall for the first time. Now begins the walk to the elevator. Depending on the settlement's layout, this may involve several hundred meters of movement across the cave floor in the suit, past storage areas and equipment yards, to the base of the vertical shaft. The lift itself is an industrial cage designed for cargo and personnel, powered by cables from the surface, controlled by an operator either in the habitat or on the pit rim. The ascent takes several minutes. Through the mesh sides of the lift, the resident watches the cave walls fall away and the circular patch of black sky at the top of the pit grow larger. At the surface, the light changes. The lift stops at a platform at the pit rim. The resident steps out into unfiltered lunar daytime, if it is daytime, and for a moment the sun is directly overhead as an unbearably bright disk against a completely black sky. The eyes adjust. The suit's visor darkens. The horizon reveals itself as a grey plain of undulating regolith, dotted with craters, stretching away to a shockingly close curve. The moon is much smaller than Earth, and the horizon feels close enough to walk to. In the sky, if this is a nearside settlement, the Earth hangs blue and fixed at whatever angle above the horizon the settlement's latitude dictates. Blue and white, cloud-marbled, still, the work of the excursion begins. Perhaps the resident is inspecting a solar array. Perhaps they are servicing a communications relay. Perhaps they are running a scientific instrument that has to be checked in person. Whatever it is done quickly, methodically, and with constant attention to the suit's telemetry. Radiation levels are monitored continuously. Any solar particle event warning would trigger an immediate abort. Any suit anomaly, a slow leak, a cooling loop pressure drop, a suspicious biometric reading would trigger the same. The resident works with the awareness that they are protected from a hostile vacuum by a machine, and that every minute the machine keeps working is a minute they get to keep breathing. When the task is complete, the resident retraces the route, back to the platform, into the lift, down the shaft, across the cave floor, dock to the suit port, climb out, post-excursion medical check, radiation dose logged, suit maintenance requested for any anomalies observed during the trip, and then, in the ordinary way, back to the day's other work. By evening, the resident is eating dinner in the galley, comparing notes with someone who spent the same day inside the agricultural bay. The excursion, which felt enormous while it was happening, has been reduced to a line entry in the settlement's log. 6 hours on the surface. 1.5 millisieverts accumulated, no anomalies. Return to routine, and this is what makes the underground settlement's life so quietly strange. The extraordinary, a trip to the surface of another world, becomes ordinary, because it has to. If it stayed extraordinary, the psychological load would be unmanageable. So the settlement's culture absorbs it. Every resident makes the trip when scheduled, does the work, comes back, and treats it as a work day. Because on some level that is what it is. The frontier is not adventure. The frontier is a workplace, with unusual hazards, unusual procedures, and unusual paperwork, and doing all of this while knowing that the settlement is not a place. It is a machine. The natural cave provides the shielding, but everything else, the pressure, the air, the water, the food, the temperature, the light, the connection to home depends on hardware that has to keep working. Every day, every hour, every second. There is no ecosystem outside the door to fall back on. There is no local biology that can help. If the settlement systems fail catastrophically, and the surface access is blocked, or the rescue mission cannot arrive in time, everyone inside dies. This is not a hypothetical to be minimized. It is the fundamental condition of the environment. The residents live with it in the same way that a submariner lives with the sea overhead, or an Antarctic winter-over crew lives with the storm outside, or an astronaut lives with the vacuum on the other side of the hatch. They live with it because they have to, and after a while they stop thinking about it consciously, and it recedes into the background of daily life. But it is always there. Now zoom out from the individual resident and look at the settlement as a whole. Consider what this represents in the broader sweep of human expansion into space. The moon was supposed to be the easy one, the near neighbour, the 3-day journey, the stepping stone. It was supposed to be where humanity practiced for Mars, and for the asteroid belt, and for whatever lay beyond, and it may still be all of those things. But if the safest way to live on the moon turns out to require moving underground, into ancient volcanic tubes whose walls have not been mapped, and whose ceilings could occasionally drop chunks of basalt onto whatever we build below, then the vision of humanity's spacefaring future changes shape. The frontier is not a shining city. The frontier is a hole. Or, more precisely, the frontier is what humans can build inside a hole that the moon happens to have carved out for them, using volcanic processes that ended 1 billion years before the first cells appeared in Earth's oceans. This is not defeat. It is not a diminishment. In some ways, it is the opposite, because what an underground lunar settlement demonstrates, if it succeeds, is not that the moon is now a place where humans can casually live. It demonstrates that humans can build a piece of Earth, a small, carefully engineered, closed-loop, radiation-shielded piece of Earth, and place it on another world. And that piece of Earth will keep working, not because the world it sits inside is friendly, but because every one of its systems has been designed, tested, delivered, and installed with the assumption that the world outside will never help. The moon does not become habitable. A fragment of Earth is smuggled inside it. The residents are not lunar people. They are terrestrials, in exile, keeping their own biosphere alive through the continuing operation of machinery brought from a planet 250,000 miles away. There is something remarkable about that, and there is also something honest about it that is worth sitting with for a moment. Because for a long time, the popular framing of space settlement has drifted towards the idea that human beings will one day become multiplanetary, that we will spread across the solar system, occupying worlds and adapting to their conditions, in the same way that our ancestors spread across the continents of Earth and adapted to deserts, tundras, forests and coastlines. The lunar cave settlement suggests that this framing is misleading. Human beings adapting to another world, in any biological sense, is not what is happening. What is happening is that human beings are transporting the specific narrow envelope of conditions in which their biology functions, the pressure, the temperature, the atmospheric composition, the radiation environment, the gravity as best as can be compensated for, and reproducing that envelope at enormous cost, inside a foreign environment that would kill them in minutes if it ever touched them directly. The envelope is what expands. The people inside remain, physiologically, exactly what they were on the day they left Earth, which means that a permanent underground lunar settlement is not a home in the way a city on Earth is a home. It is more like a research station that never closes. Its residents rotate in and out. Some of them stay for years. A few, in the longer-term concepts, may live out their entire adult careers there, and in the very longest-term concepts, a small number may raise children inside, though the medical and ethical questions surrounding that possibility are enormous, and the effects of 1/6 gravity on prenatal and early development are completely unknown. But even in the most successful version of the settlement, the connection to Earth remains total. Every kilogram of imported hardware, every message from a family member, every replacement filter, every scientific instrument, every visiting crew member, arrives from a planet that is still, and probably will always be, the only place where the settlement's residents can actually walk outside without protection and simply breathe. And that, in the end, is the honest shape of the story. The moon is our nearest neighbour, the world we know best beyond our own, the place we have already visited and returned from, and humanity's first realistic path to living there permanently may run not across the plains that the Apollo astronauts explored, but beneath them. Down through pit skylights carved by ancient collapses, across debris fields of tumbled basalt, into cave conduits that have been sealed since the last lunar eruptions cooled, inside modules that hold their air against a vacuum on one side and stable rock on the other, under a ceiling of volcanic stone that provides, for free, the shielding that would otherwise require moving a small mountain. And inside that shelter, a small community of human beings, doing every ordinary act of human life, sleeping, eating, exercising, working, arguing, laughing, calling home under artificial light, in recycled air, in 1/6 gravity, with the surface of the moon somewhere overhead and the surface of the Earth 250,000 miles away, hanging fixed in a black sky that the residents themselves will rarely see. That may, in time, become a place. It may become the first lasting human community on another world, but it will not be a city on the moon. It will be a sealed transplant of Earth's own biosphere, buried inside the moon and protected by the moon from the very environment that the moon itself provides. Its residents will spend most of their lives surrounded by rock. They will never feel wind. They will never feel rain. They will never step outside without carrying a complete personal life support system, and even then, only briefly, and only under strict medical supervision. And that is what living on the moon would actually be like. Not a shining base on a bright plain, but a sealed shelter beneath one. Not an open frontier, but a small industrial cave, dependent for every breath and every litre of water and every kilowatt of power on machinery that has to keep working. Not a second Earth, but a fragment of Earth, smuggled into the rock of another world, kept alive by the constant, careful attention of the people who chose to live inside it. The safest way to live on the moon may indeed be to retreat beneath its surface. That retreat may become, in the coming century, the beginning of humanity's first lasting home beyond our own planet. But it will not make the moon habitable. It will only make it possible to survive there. And the difference between those two words, habitable and survivable, is the difference between a place where you belong and a place where you have brought your belonging with you. The moon is not our second home. It may one day soon be the first world we successfully hide inside. And the people who live there, deep beneath a plane that Neil Armstrong and Buzz Aldrin walked upon nearly 60 years ago, will do so knowing that everything they need to stay alive came from somewhere else, and that everything outside their walls is trying, patiently and endlessly, to take it back.